Here's a shortcut that you can use when you're testing whether sentences are truth functionally equivalent. So remember the characteristic truth table for the biconditional, right? It is true whenever two sentences have the same truth value, and it's false whenever they have different truth values. Now, the implication of that is this: if P and Q are truth functionally equivalent, then their biconditional is going to be truth functionally true, right? If P and Q have the same truth value on every single truth value assignment, right? So they're truth functionally equivalent, then their biconditional is going to be true on every single truth value assignment, which means that it's going to be truth functionally true. So the way that you can test then whether they're truth functionally equivalent is by forming their biconditional and testing to see if their biconditional is truth functionally true. And this is typically easier than just testing directly for truth functional equivalence because the final test that you have is usually easier to do, right? Instead of going through line by line and verifying, okay, they're both true here, they're both false here, et cetera, et cetera. You just basically just scan your final column and verify, is this all T's or do you have some F's mixed in there? Okay, so for an example of this, let's go to the generator. We'll start with these two sentences here. Let's suppose that, okay, so when we were talking about symbolization, I said that these are two alternative ways that you could symbolize neither nor. Let's say you wanted to fact check me on this and verify that these are actually equivalent. Um, so to test the equivalence of these, what we'll do is we'll form their biconditional. And in order to make this into a well-formed sentence, we will have to put parentheses around this. Remember the other side, right, with the negation there, that does not get parentheses because there aren't parentheses around negations. Then generate the table, and here you go, right? It's true in every row is true. That tells you that these two sentences will have the same truth table or truth value on every possible arrangement of atomic components, and thus every possible truth value assignment. There's another shortcut that you can use to test entailment. So remember the characteristic truth table for the material conditional. So this is false if the antecedent is true and the consequent is false, and then it's true in every other case. Now, a set will entail a sentence if whenever every member of the set is true, then that sentence also has to be true. And it fails to entail that sentence if whenever every member of the set is true, that sentence is false. So um, you can test this by forming what's called, well, first of all, let me specify if your set is finite, then you can test for entailment by forming what's called a corresponding material conditional. So if you've got a finite set that runs from P1 to Pn, then what you do is you form a conjunction out of all the members of the set, right? The conjunction P1 and P2 and et cetera, all the way to Pn. Form the conjunction of all of those. That is the antecedent of the conditional. The consequent of the conditional is Q. Um, if the set entails the sentence Q, this conditional will be truth functionally true, right? If it's the case that every time every member of that set is true, Q has to be true, then this material conditional is going to be truth functionally true. And if it's possible for every member of that set to be true and Q is false, then there's going to be at least one line in the truth table for this material conditional where this material conditional turns out to be false. So what you can do is you can test for entailment here by forming this material conditional and then just looking to see if this is truth functionally true. And this is another one of those cases where it's a little more difficult to set up the the truth table and run the generator, but it's easier to read the output because again, all you're doing is you're looking at one column and you just need to determine if every member of the every every letter in that column is a T. So we'll look at an example. Let's go to the generator. So here is our set right here. It's these sentences: B and K, if N, then not K, K or not K. And then we're going to look to see if it entails this sentence here: if B, then N. So out of these first three, we need to form a conjunction. So we'll start by putting them all in parentheses. And then we're going to form conjunctions out of them. Now, if you remember, we talked about how there's this informal convention that you can drop the if you've got a string of conjunctions, you can drop the internal parentheses because it doesn't matter where you put them. That is this informal convention. Sometimes people follow it, sometimes people don't. You can't use that in this generator. You have to put in the internal parentheses, right? Each conjunction only gets two, can only have two inputs. If you leave out the internal parentheses, it will just give you an error and tell you that you don't have a well-formed sentence. So here we have it set up so that each of them only has two, and I believe we're missing a set of outer parentheses, so we'll put those in. Then we need to put in the conditional and the parentheses around that. And let's see if what we have is a well-formed sentence. And it is. And what we can also see here from this is that the entailment fails, right? So this is the corresponding material conditional, but it's not truth functionally true, right? When B and K are true and N is false, then it's possible for if B then N to be false when every member of the set is true. And so we've established then that this set does not actually entail this sentence. Here's a shortcut for testing for consistency. So remember the rule for conjunction, right? If there is a row of the truth table where both of the conjuncts are true, then the conjunction is true. Otherwise, then the conjunction is false. And this applies actually if you add more conjuncts than just the two to the conjunction, right? Like if we were to take, we've got P and Q, right? If we were to have P and Q and R, then what's going to happen is the only place where it can be true is here in this row here where P and Q is true, and then also where R is true. So you're going to have the same thing, right? The conjunction will only be true where all three of those sentences are true, P, Q, and R. And this is actually just, if you have a string of conjunctions of sentences, then no matter how many sentences you have there, the conjunction is true only when all of those sentences are true, and otherwise it's false. Now, what that ends up telling you is this. Suppose you have a set of sentences, and then you make a conjunction out of all of the sentences in the set. And then the set, of course, has to be finite because otherwise your conjunction would be infinitely long, which SL doesn't allow. If the set is truth functionally inconsistent, then there won't be a row of the truth table where all the members of the set are true. And what that means then is that this conjunction will be truth functionally false because there will not be a row where every conjunct in that conjunction will be true, which is the condition that you need for the conjunction to be true at that row. And if the set is consistent, then there will be at least one row where this conjunction is true. So that conjunction is going to turn out to be truth functionally indeterminate or truth functionally true. But the important thing is that there's going to be at least one row where it turns out to be true. So let's look at an example of applying this. We'll test this set here for consistency. Okay, so we're here at the truth table generator. So here's the set members that we've entered in. So what we need to do then is convert this into a conjunction. So we need to put parentheses around both of the sentences so that it's a well-formed conjunction, and then we put an ampersand in between them and hit generate table. And then what you can see is that the set is consistent because you've got these three rows here where you have t's, right? The conjunction of the two of them is truth functionally indeterminate, which means then that the set is consistent. If we were to take another set, let's say we take this one here. We'll go A, not B, and if A, then B. Now, if you remember the truth table for the conditional, you should be able to tell that this is going to be inconsistent, right? When A is true and B is false, then if A, then B has to be false. So you can't have all three of these being true at the same time. So now we'll go through and we'll form a conjunction out of all of these. And this is a little bit trickier to do, of course, because there's three of them. And then we will need another set of parentheses here. And actually, the trickiest part when you're doing this is always making sure that you've got the parentheses lining up. And I think that's good. We'll generate this, and yeah. And then if you look at this, you get the result. So this conjunction here, this is truth functionally false, which means that this set is inconsistent, which is exactly what we expected.